AP Calculus AB, we're looking at analytical and graphical connections between a function, its first derivative, and its second derivative. Logically speaking, the second derivative is the first derivative of f prime. So the same relationship that exists between f and f prime must exist between f and f double prime. Let's see if we can figure out this table. If f double prime is equal to 0 or is undefined at x equals a, then f of x has a potential point of inflection. So let's just say, for less words, may have a point of inflection x equals a. And f prime also may have a point of inflection. Not guaranteed, but it's possible. If f double prime is bigger than 0 at x equals a, so it's positive, then it tells us that the original function f is concave up at x equals a, and that means that f prime is increasing at x equals a. If the second derivative is less than 0, if it's negative, then the original function, f of x, is concave down. I'm missing an is in here. Picklesworth. And f prime is decreasing. Let's fix this a little bit. Put an is. The President of the United States was once confronted about something, and I believe his answer, I won't tell you the question because it's a little controversial, was it depends on what the definition of the word is. I thought of that with all these is's. What if the second derivative changes from positive to negative at x equals a? What's that tell us about the original function? Well, that tells us the original function has a point of inflection. There's a point of inflection. There's no doubt that x equals a. Same can be said if f double prime changes from negative to positive. It means there's going to be a point of inflection on the original function. And if f double prime changes from positive to negative, that means f prime is going to have a relative minimum. And here, if f double prime changes from negative to positive, then f prime is going to have, I'm sorry, I said minimum here. This is a relative maximum. My apologies. This one's going to be a relative minimum. All right, so let's see. Let's consider the function. Notice that there's a calculator sign here, which means you can use a calculator. Consider the function h prime, which is 2x minus x sine of 2x on the open interval from -5 to 5 to answer the following questions. Based on the graph, how many relative extrema does the graph of h have? Let me bring this graph in. I'll be moving this around so we can see this. Actually, I'll put it up here for now. I won't. I'll put it right here for now. Based on this graph, how many relative extrema does the graph of h have? Well, looking up here, if we want relative extrema, we want to look how many times does this graph cross the x-axis? Crosses the x-axis once. So in other words, h prime of x is equal to 0 one time. Therefore, we expect h of x has one relative extrema. Based upon the graph, how many points of inflection does the graph of h have? Well, that is determined by the relative extrema of h prime. Remember, this is h prime down here. This has an extreme value here, a relative extreme value, 1, 2, 3, 4, 5. Something weird's happening here, but there's no extreme values. So we could say h prime has 5 relative extrema on the interval from -5 to 5. So we can conclude from that lights flickering off in here, freaking me out. We can conclude from that that h has 5 points of inflection. Let's get rid of this graph. 3 says find the equation of h double prime and then graph it on your calculator. Well, let's see. Let me bring this h down here. So h double prime all right, h prime prime. This is the power rule. It's just one function. This is going to be the product rule, and this also here is going to be the chain rule. So we've got a lot of stuff going on here. Power rule, derivative of 2x is just 2. We are subtracting from that whatever this derivative is, and so I'm going to put this in brackets. The product rule, take the derivative of the first, which is going to be 1, times the second, sine of 2x, plus the first, x, times the derivative of the second. This is going to be the chain, so the derivative of the outside is cosine. Inside stays the same. Since it's the chain, we then multiply it by the derivative of the inside. The derivative of 2x is 2. So to be clear, this is not part of your work, but this was the product rule. Just writing this for your notes. And this part right here was the chain rule. Simplifying my signs a bit here. And I could say that h double prime is equal to 2 minus sine of 2x minus 2x cosine of 2x. And then I want to make sure I put this in right into Desmos. I did not. I did not put that in right. Let me take a picture of this. And let me bring that in here. It says to graph this on your calculator. Well, this is my calculator. Explain why the graph of h prime confirms your response to question 2 above, h double prime. Looking at this graph, sorry, I'm losing my touch here. My answer to number 2 was h has 5 points of inflection. Now if we look up yonder, up here, we have points of inflection every time the second derivative changes signs. So how many times do we change signs here? Keep in mind this is h double prime. Changes from negative to positive. Changes from negative to positive here. Positive to negative. Negative to positive. Positive to negative. Changes signs once, twice, 3, 4, one more over here, 5 times. And we said up here there were 5 points of inflection. So confirmed. So to write this out, we could say h double prime changes sign 5 times. Therefore, h has 5 points of inflection. We are trying to make connections between the first derivative, second derivative, and the original function. That is what our goal is here. All right. I'm trying to separate my work because stuff is kind of jamming together. On the flip side, see how many of these things we know. Based on the relationships that we've seen from the first, second derivative, let's see what connections we can make. If f is increasing, what's that tell us about f prime? Well, if f is increasing, it means it's going up. That means the slopes are positive. That means f prime is bigger than 0. If f is decreasing, it means the slopes are negative, so f prime is less than 0. If the original function has a relative min or max, then f prime is either going to be equal to 0, or it could be undefined if it's a cusp or corner point. If f of x has a point of inflection, then f prime is going to have an extrema. If f is concave up, then f double prime is bigger than 0. If f is concave down, f double prime is less than 0. If f has a point of inflection, then the second derivative is either equal to 0 or it's undefined. If f of x is increasing, then f double prime is bigger than 0. So keep in mind, once we get to this point here, we are repeating answers because the relationship between f and f prime is the same relationship that f prime has with f. F prime is decreasing, then f double prime is less than 0. If f prime has a relative maximum or minimum, then f double prime is equal to 0 or undefined. If f prime has a point of inflection, then f double prime has an extrema. It's actually pronounced extrema. Extrema sounds funnier. If f prime changes from negative to positive, then f has a minimum. Let me be more specific, a relative minimum. Got to use my words right. If f prime changes from positive to negative, then f has a relative maximum. If f prime has a relative maximum or minimum, then f has a point of inflection. If f double prime changes from positive to negative, then f prime has a relative maximum, also known as the local maximum. If f double prime changes from negative to positive, then f prime has a relative minimum. Look, it's only 16 scenarios. Here's what I'd like you to do. I'd like you to stop watching this, and I'd like you to see if you can complete this activity. On the following pages, you will find 15 graphs of polynomial functions. The 15 graphs can be put into 5 groups of 3, so that the 3 graphs in each group would represent f, f prime, and f double prime. Once you've graphed the groups, record the groups in the table to the right using the numbers 1 through 15. This works best if the graphs are cut out so that students can arrange them in different groups. Well, if you're at home right now, I'm sorry, that can't happen. If you're at school, then I probably cut them out for you. If you got a printer at home, print these out, then cut them out. A couple things I want to make a note of before you start this. If you're taking the derivative of polynomial functions, and if you look at all these are all polynomials. Every time you take the derivative, it decreases by 1 degree. So in other words, let's say that you think this is f, which is a quadratic, it appears to be, then its derivative has to be linear. This is linear. Maybe they go together. Maybe they don't. Let's say that you have a quartic function, degree 4. Then its derivative has to be cubic, although I'm not saying this is the actual cubic one for this one. Something else I want to point out, let's say that this is f or f prime. F double prime would have to be below the x-axis here because this graph is decreasing, have to be above the x-axis here because it is increasing. So let me let you to that. I'll make a separate video over the answers and you can see how you did. Actually, no, just pause the video and then come back and you can see how you did. And we're back. Let's say that you did your f of x. You did the first one is 2. Its derivative would be 13, and its second derivative would be 7. Let's just examine that real quick. So here's function 2. 13, I'll tell you what. Let me take 2. Let me paste it right here. Let me take 13. Let me paste that beside it. And let me take 7 and paste it beside that. Let's just examine these 3 and see if this makes sense to you. Here's one thing that makes sense. Cubic, quad, linear. That makes sense. How about this has an inflection point right here? This has a minimum at that same x value, not a coincidence. This is concave down. This is decreasing. This is concave up. This is increasing, not a coincidence. Here the slope's positive. This is above the x-axis. Here the slope's negative. This is below the x-axis. This is increasing. This is above the x-axis. None of that's a coincidence. Comparing these two, we have a, well, let me go back to this again real quick. We have a relative extrema. On the derivative, those are x-intercepts. Same logic here. We have a relative extrema on a second derivative of the original function. That's going to be an x-intercept. The slope's negative. This is below the x-axis. Slope's positive, above the x-axis. That's just one example. Hopefully that made sense. Another combination is 4, 5, and 8. Another combination is 9, 12, and 3. Another combination is 10, 1, and 11. Another combination is 15, 6, and 14. This would take, to do this, probably 20 minutes in a group. By yourself, it might take 30. So hopefully you stopped the video and you tried. Once you saw this first example, hopefully you stopped, checked out some others. That concludes these notes. Thank you very much.